Hello! This video starts talking about existence and uniqueness, and we're talking about it following the book section 2.4, that is the comparison between the linear case and the nonlinear case in first-order ODEs. We're trying to understand what is the difference between these two cases and how does it impact our existence and uniqueness understanding. So first, what is the existence and uniqueness problem? The problem is that we have y prime equals f of x and y. We know nothing about it, and we wonder if it has a solution. So can we actually go out and look for a solution and expect to find something? And do we know if it has a solution? And after that, do we know if there is only one solution? So shall we stop after we find one solution, or shall we keep going? Think of it as when you're solving an algebraic equation, you know that first order algebraic equations, so m of coefficient times x plus other coefficient equal to 0 always has a solution. But if you're going to second order, you might have no solutions, one solution, or two solutions. For example, if you have x squared equal to 0, that has only one solution. But if you have x squared equals to minus 1, there is no solution. Well, if you have x squared equal plus 1, it has two solutions. So we are trying to bring that understanding from algebraic equations into ODEs. When can we be sure we don't even have to look at the equation because it has no solution? Or when can we be sure we got all of them? So let's first focus at the more restricted case, that is the first order linear ODEs. We couple it with the initial conditions, so we have y prime plus p of t y equals g of t. And we fix one point that we call the initial condition. We know that y calculated at some time t0 has a specific value y0. The theorem states that a solution of this problem exists and is unique for t in an interval around t0. So from t going from alpha to beta, where alpha is smaller than t0 and beta is bigger than t0. So we need that p and g are continuous in the same interval of t. So p needs to be continuous between alpha and beta, and g needs to be continuous between alpha and beta. P could be continuous on a bigger set, but if g is not, that is the boundary we need to respect. That means that if p and g are continuous just a little bit around t0, that's what you have to stick by. If p and g are continuous in a bigger interval, that's the thing you can expect to find. Let's look at an example. We're looking at y prime plus 1 over ty equals 1 over t squared minus 1. And we fix an initial condition at time equals to 1/2. Then we look at p and g. In this case, p is equal to 1 over t. And we look at it and we notice it's discontinuous at t equal to 0. And g of t is 1 over t squared minus 1, that is discontinuous at plus and minus 1. Discontinuous in the sense it tends to infinity, so we cannot go through it. That means that a solution to this problem, even if we're not able to calculate it, even if we can only give integrals but not explicitly write it down, a solution exists and is unique for t between 0 and 1. Outside of that area, we don't know if it exists or not. We don't know if it's unique or not. Well, part of your equation tended to infinity, so probably you're not going to be finding it outside. Let's look at another example. Y prime plus sine of t times y equal cos of t, with an initial time at 73 in which y is equal to pi. So in this case, pt, according to our nomination, is the sine of t. G of t is equal to the cosine of t. Both of them are continuous for all values of t. So it doesn't even really matter where you started your initial condition. There is a unique solution for all values of t.